Hi, I'm Keith, but some people know me as One Said Cookie. If after the presentation you want to follow me on social media, that's how you do it on Mastodon. I fully expect that none of you will want to be associated with me at all after you've seen what I've got to say, but you know, it takes all types to make a world. I'm afraid Bok somewhat lied to you earlier. I'm not actually here to talk about what he said. I'm here to tell you how to write Hello World in Swift. It is an extremely advanced topic, and I hope that everyone will have a lot to learn today. So the first thing that we have to understand when we want to write Hello World in Swift is how we're going to manage text encoding, because we've got to output a string. This is not updating. Bok, my slide is not updating. There. Just does. Oh, there we go. This time it's fine. So basically, in order to output a string, we're going to need to, it's equivalent to outputting a sequence of numbers. Hello world, we can output this sequence of numbers, and that will do the job. Now, we're programming Swift, and all of us know that the most important things in Swift are type safety and data modeling. So the first thing that I want to talk about is how we're going to represent these numbers that we need to output. Thankfully, there's this. Thankfully, we've got our old friend Piano and his axioms for the natural numbers to fall back on. And so we're going to define 0 as an empty structure conforming to the empty protocol nat. And then we have the successor function. You can think of successor as adding 1. So every natural number is either 0 or 1 more than another natural number. Here, the pred in the generic parameter of that successor type. So, for example, it's still really laggy. I need to press the next slide button about 10 seconds before it's required. I blame Apple. That's still the old frame. There we go. So here we can type alias 1 as the successor of 0, type alias 2 as the successor of 0, 3 as the successor of the successor of 0, and basically, as you can see, the bigger the number, the more the suck. Now I'm going to add a little convenience to this, because ultimately we kind of do have to be able to see what we're doing. So I've made a static, of course the slide hasn't updated yet. I'm going to make, in several minutes, a static value property on the NAT protocol and implement that to return 0 for the 0 struct, and implement that to return 1 plus the predecessor's value for the suck struct.
I've never seen it do this before.
Well, it's probably I'm probably doing it wrong at this end. Yeah, there we go. Perfect. I can go out of full screen.
Try and move, like, see if it
Yeah, maybe that's fine.
Yeah, that says the one.
Yeah, that's the same thing. Okay, now that we've got numbers, we move on to strings, and we can define strings in exactly the same way. So a little protocol, again with the static value. An empty string is just an empty struct that conforms to that protocol, and when we want to append a character onto a string, we do so by using our natural number for the character that we're adding and the prefix. And notice that this makes strings kind of backwards. The last character of the string is on the outside and the first character is on the inside. That's pretty convenient. So here's how you do it. A is ASCII 6, capital A is ASCII 65, capital H is a few beyond that, and I is a little beyond that, and then you can see that H and I are backward, and if I print out their value, I'll get high. Beautifully type safe, really, really difficult to mistake one string for another in this case. The compiler will just tell you, no, that is not the right string. But I think you'll agree with me that writing hello world like this is going to be like terminally sucky. Incomprehensibly sucky. So as we know, whenever we hit a problem where the language isn't quite expressive enough, we need to do some metaprogramming. So we need another language that's going to help us to program hello world more effectively. And I've chosen the well-known language Brainfuck. I apologize to anyone who is offended by this word. I'm going to be saying it a lot. It's going to be on my slides a lot. If you do, put your hands over your eyes and ears if you're that. So Brainfuck is a little esoteric language. It consists of 8 instructions, of which I'm only going to use 7. Those are represented by those little symbols. It has an instruction tape which can move left and right around the instruction pointer. And it has an infinite data tape full of zeros at the start, but each cell can hold an arbitrary number. Here, copied and pasted from Wikipedia, the actual instructions. So there is one to move the data pointer left and right along the data tape, one to increment and decrement the value on the data tape at the current data pointer, one to output the current cell on the data tape as a character, one to accept a byte of input, which we're going to ignore because we have no way to accept any input whatsoever, and then a pair of matched square brackets, which act as a kind of combination if and while loop. And this on the right, eventually, no, not eventually.
Did your mouse pointer move?
Did my mouse pointer move? Yeah, I got to keep wiggling. Okay. So on the right is the Hello World program that is going to help us to generate Hello World in Swift. On the left is the same thing with comments. I hope that you all read that real quick because there will be a test after the show. So, in order to use this metaprogramming technique, we're going to have to implement a Brainfuck virtual machine in Swift. So first of all, I've got the memory tape, the data tape. This is represented in exactly the same ways as the numbers and the strings, except that it goes both directions. So I use 2 half tapes, one to the left, one to the right of the current head position. And a square, once again, it has a natural number in the square, getting maximum use out of Peano's axioms. Then on the instruction tape, we need all the different instructions that you saw in the table from Wikipedia earlier. Wiggle. You'll notice I've added 2 protocols because loops are not simple, and a new instruction to represent the end of a sentinel at the ends of the instruction tape called exited, and that's what I'll use to know when my Brainfuck program has finished. But otherwise, wiggle. The program tape is exactly the same as all the other things you've seen so far. It's either the end of the tape or it's an instruction and some more tape. And then, having done that, we can make the machine. So the machine consists of the data tape to the left, the value of the current cell, the data tape to the right, the program tape to the left, the instruction in the current program cell, and the program tape to the right. I'm not in this presentation going to talk about the state stack. That is a complicated thing to do with pulling while loops back to the beginning of the loop, and it's kind of not relevant to your enjoyment of this. But output is the values that have the string that has been output so far using that dot instruction. And the body of this contains a variety of subscripts, all of which look like this, basically. So I'm not going to go through all of them. That would be very boring. But here's one so you can see it, and I will explain later why it looks like this, because it certainly looks weird. But I'd like to draw your attention first to the middle block, where I've put the arrow pointing to the conditions of the current state of the machine. So the important one here is that this subscript only applies when program write has one more instruction and the program current instruction is increment. And then we see the next state of the machine, so it still has the same left and right of the tape, but it's used suck to add 1 to the current value on the tape. It has moved the current instruction off to the left of the program tape, and the next instruction into the current position, but then the right of the program tape is bumped up, and we haven't changed the output or the state of the machine. And amusingly, this function just fatal errors. We are never going to call this function, and that is true of most of the functions in this program. And then there's 18 more of those, and I'm not going to show you them all. Wiggle. 18 more of those. I'm not going to show you, but I will give you a link to go where you can go get the code if you really want to see them all and all the details of how the while loop works. So let's talk about why it is that weird. And why it is that weird is that I need to use this dynamic member lookup feature of Swift. So dynamic member lookup is a feature which allows you to effectively use the properties on one type to define computed properties on another type. So here I've defined a struct A with a property A, which has the value 3 always, and a struct S with the dynamic member lookup attribute. And then I provide this subscript, which takes a key path from, in this case, that other simpler A struct and returning an integer. And then this property will return an integer, and the implementation is kind of unimportant. So when I do s.a down here at the bottom, I'm going to get 3. And the reason I'm going to get 3 is that the compiler is going to look for .a on my struct s, and it's not going to find it because it's not there. And so it's going to translate that .a because it's got a dynamic member lookup attribute. It's going to translate that into a call to my dynamic member subscript. And it's going to turn that .a into a \.a, just a key path literal, and pass that to my function. So in this case, that's pretty simple. But we can also use it to infer the return type from the key path. So here, the only difference to the previous slide is I've added this generic t, which is then the return type of the key path and the return type of the property on this thing. So once again, we're still getting an int because the underlying property is just an int. But then things get interesting. So what if I have 2 dynamic member subscripts? This top one is the same as the previous one, but I've added a generic parameter to my struct with dynamic member lookup. This top one is the same as the other one, but only triggers where my generic parameter is integer. And then the bottom one triggers where the key path is to a particular specialization of myself, where the generic parameter is something else. So I can here construct an s of float, and I can still do s of a, and this will convert it, same as it always did, into a call to the dynamic member subscript, which is going to hit this one because g is float. But then it's going to find out that this key path literal, \.a, was actually a key path into s of int t. And then it's going to go look again recursively for another property, this time on s of int, and this time it's going to find the first overload because now the key path is relative to a. So this allows me to force the compiler to recursively search through all these different properties at compile time. And that's why there were 18 of these subscripts, because there is one for each transition in the Brainfuck state machine. And I'm going to use these preconditions in the dynamic member lookup to make it, when I go dot output, it's going to go one step through the state machine, find that there's no output property, go another step through the state machine, find that there's no output property, go another step through the state machine, find that there's no output property, until we hit the case where the current instruction is that special sentinel exited instruction to say that we've come to the end of the program. And there I define the output property. This output is still fatal error. I'm not going to call this property, but that output is going to contain that string that we've built up through all the output instructions, through all the previous iterations of that stepping through the Brainfuck program. And then there's a stupid little trick here which allows me to infer the type of this of this associated type from an initializer of a static variable which never runs. So although this looks like I'm calling .output, so long as I never refer to this infer from variable, .output will never be called. But the type of this infer from variable is whatever the type of this .output property is. And then I can just print the type if anyone wants to see that, which they don't, and the value. So, beautiful. There's the setup. There's the Hello World program from earlier. Here is the machine type with all of those instructions converted to the Swift type system. And now I'm ready to go compile that, and I'm going to see this finally print Hello World. Wiggle. Well, Swift doesn't really like it when you put like two equal equals with an ampersand between them, so I guess I probably should have expected that this was like a bit too much. Okay. So what if I delve into the source and find some obscure compile time options that let me give all the time and memory in the world to the type checker? 4 gigs of RAM and 20,000 seconds. That should be plenty, right? Yeah, not so much. Well, so it turns out like in ASCII, uppercase letters have lower values than lowercase letters. So actually yelling reduces the amount of computation that I have to do. And also if I write something shorter like hi Swift instead of hello world, then it dramatically reduces the amount of computation that I have to do. So here's a program that's going to print hi Swift. And if I hit compile on this one, wiggle, 56.1 seconds later, compilation succeeds. This is actually slower in Xcode 16 because I ran it last night. It takes 67 seconds in Xcode 16. And we've got hi Swift. So, in conclusion, you now know how to write the world's worst Hello World program. It takes nearly 4 gigabytes of memory and nearly 1 minute to compile on an M1 MacBook Pro. It doesn't even print Hello World. But you do at least know that Swift's type system is Turing complete, which I didn't before I started this exercise. If you want the code, wiggle. That's the thread to go to. You'll find... No, please. You would have to be insane. I don't expect anyone wants this code. There it is, if you want it. And apparently that is the end of my presentation.
Does anybody have any questions? Okay, show of hands who actually understood some of that. Got the high Swift bit? Yep.
What made you even like try to write this? What sparked your curiosity to get that far?
I accidentally created the dynamic member lookup device, trying to do something simpler. And I realized that when I accidentally used it to reverse one of those lists, like the natural numbers or the string. Pretend I accidentally reversed a string, which I'd been building for some entirely other reason. But I accidentally reversed a string, and I was like, I'm pretty sure that means that Swift's type system is Turing complete, which was not a fact that I knew at the time. I now know that some people did know that ahead of me. But as far as I know, like this was the first proof, like solid proof. People had hand waved and said, "We're pretty sure this is the first solid proof that this Swift type system is Turing complete." And it was also the first usage of that dynamic lookup device.
So you went on a mission to prove that it was true.
I hit that hunch, and then I was like, I have to get to the bottom of this. Yeah.
What was the reaction to your forum post?
Pretty good. People liked it. It's pretty niche content, honestly. Like,
we were still very desperate to get you to present about it here, though, because it is something nobody would ever think of normally. So, does anybody have any questions with Keith's laptop dying?
my laptop is apparently over.
Oh.
What practical use can you do with this?
So, what it proves is that anything is possible, right? So, whatever you thought you could, however you thought you could build an API to constrain uses to certain ways, like, technically that is possible. Whether you can get that to compile in reasonable time is a totally different question. But, like, if you were thinking you'd like to build a system that can't be misused in particular ways, you definitely have the power to do that. Practicalities are basically still eluding me at this point.
Is Swift's type system deliberately Turing complete?
I don't believe so. I think that they intended to keep it from being Turing complete, if anything. There are other formulations of Turing completeness. You do not require the dynamic lookup device in order to get Turing completeness.
Are there other programming language type systems that are known to be Turing complete?
Yes, lots of them. C++ is, Rust is, TypeScript is. So it's pretty common for the more expressive programming languages to have Turing complete type systems. Turing completeness also turns up in all sorts of other places, like Magic the Gathering is Turing complete, PDF is Turing complete. It crops up in all sorts of places you don't necessarily expect.
Are there any other even more esoteric languages that you'd like to work with?
Brainfuck was complicated enough, thank you. Malbolge holds a special place in my heart, but I don't think anyone's written Hello World at all in Malbolge yet. So, that is a self-modifying. It's similar to Brainfuck, but it's self-modifying. So every instruction that you run actually modifies the program itself. So you kind of very difficult to predict what the rest of the program is going to do. Any more?
Just checking if there's anybody online. No, don't do that. No questions online. Maybe a suggestion for Lisp, but yeah.
I'll keep it in mind.
Cool. Thank you very much, Keith.
Thank you.